My name is Christina Peterson, and I'm presenting my paper, Durable Correctness Verification Tool. Non-volatile memory, abbreviated NVM, and it's also referred to as persistent memory, provides high-performance persistent storage that's byte addressable and has access latency close to DRAM. There's many benefits to persistent memory. These include the ability to maintain persistent data, with faster access times in comparison to storage. It's also energy efficient because it eliminates the need to refresh the memory cells. And it also provides quick recoverability in the case of a power failure or a crash. One of the main challenges with persistent memory is that the caches and registers are expected to remain volatile, which can lead to data inconsistencies following a crash. So as a result, there have been correctness properties that have been defined to be able to guarantee consistency properties of following a crash event. Crash consistency is a property of NVM systems where the data is recoverable to a consistent state following a crash event. So the instruction set architecture for persistent memory has provided instructions to allow the programmer to ensure crash consistency. These include cache line writeback, which enforces data writeback to persistent memory, sfence, which ensures a strict ordering between persist before and after the fence, and then the combination of the cache line writeback and the sfence is a persist barrier. These instructions are very expensive and can degrade the performance. And so the designers often use these to persist just the bare minimum information so that a data structure can be reconstructed using a recovery procedure. Designing persistent data structures is challenging because they need to simultaneously address crash consistency, performance, and scalability. The persist ordering problem is when a cache side update occurs before persistence. So in this code example, there's a compare and swap that changes a current node's next pointer to a new node. And if that succeeds, it's going to call a cache line writeback on that next pointer and then an sfence. So even this simple code can result in inconsistencies. So in the diagram, the initial state is that node A is connected to node D, and it's persisted. So then if another thread comes in and inserts node B, and then that's done cache side and it's delayed. And then another thread comes in and inserts node C and that's persisted. And then there's a crash. The link from node A to node B is lost. And so now this is in an inconsistent state with some prior state before the crash. So this is an example of crash consistency violation. So there's been correctness conditions that have been defined to formalize durability. One correctness property, which is very well known in for multi-core programming, is linearizability. It's a correctness condition that such that the history of method calls is equivalent to a legal sequential history, and each method call takes effect at some instance between its invocation and response. So the analog of linearizability for NVM systems is durable linearizability. And this guarantees that the state of a data structure following a crash reflects a consistent subhistory of the operations that completed before the crash, and possibly may include operations in progress when the crash occurred. So here's an example of a persistent queue, and then the enqueue operation is shown in the left. And this is going to showcase an example of a durable linearizability violation. So first at line 7, there's a cache line writeback for the node that's going to be enqueued. And then at line 11, we do a compare and swap to change the next pointer of the tail to that new node. And then at line 13, we have a cache line writeback to persist that next pointer and then an sfence. And then at line 14, we do a compare and swap to update the tail to this new node. If the compare and swap fails, then we have to do a cache line writeback at line 17 for the tail's next pointer to help finish persist that previous operation and then update the tail. So in the right, there's a history that shows what can go wrong. So thread 1 first accesses the tail, which is pointing to just the head, and this queue is initially just has the head in it. So the next pointer is null. So it's going to do a compare and swap at line 3 to update the next pointer to node A, and that succeeds. And then it does a cache line right back to persist that link. Then at line 5, thread 2 comes along and it reads that the tail is pointing to head, but it sees the next pointer as node A, and so it's going to try to change the next pointer from node A to node B, and this is where things go wrong. At line 8, then we do a persist for that next pointer, and we persist the tail's next pointer to node B, and then at lines 9 and 10, we update the tail. So we've lost the operation by thread 1 where they enqueued node A. And so this is a violation of durable linearizability. However, this is actually crash consistent because it's consistent with some state that occurred prior to the crash. And so this is the type of violation we want to find, which is violations of data structure semantics. So this was actually a very simple mistake. At line 11, there was we needed to check that next was equal to null prior to updating the tail's next pointer, since the tail hadn't been updated in the previous example, and so that would have made that code durable linearizable. So there's some key challenges facing durable correctness verification. The existing tools for checking durability properties, which include YAT, PMCheck, Persistence Inspector, and PMTest, and XF Detector, these all focus on crash consistency, but they don't check durable linearizability. XF Detector can detect semantic bugs, but these semantics are limited to crash consistency mechanisms, including undo logging, redo logging, checkpointing, or shadow paging. So they're not able to check data structure semantics. And only YAT and XF Detector can check the correctness of the recovery procedure, which is very heavily used in persistent memory design. So there's also some challenges facing concurrency verification due to all the ways the threads can interleave. So verifying a concurrent history for serializability, sequential consistency, or linearizability is NP complete, and proving that a concurrent system is sequentially consistent or linearizable is undecidable. So for this work, we propose vector space verification durability. This is a technique that expresses durability properties of concurrent systems in vector space to reduce the time complexity of verification. So the correctness properties that we want to express include atomicity, data structure semantics, method call ordering, and durability of method calls. And the way that we're going to do this is by representing the method calls in vector space as column vectors. And each index in that column vector corresponds to an object item combination. So we're going to use a priority system. If an item has the highest priority to be removed from an object O, and I is that corresponding object item configuration, then VI equals 1. If an item has the lowest priority to be removed from an object O, then VI equals 0. So there's going to be many priorities in between the highest and lowest according to method call ordering and data structure semantics. So the way that we're going to handle this is through a geometric series 1/2 to the n. So an item is initially assigned a value of 1. And then if an item is determined to have a lesser priority, then it's going to be demoted by subtracting 1 minus 2 to the j. And then if that item is removed from the objects, all the items that had previously been demoted have to be promoted back by adding 1/2 to the j. So here's an example to illustrate this theory. So we have a FIFO queue concurrent history, and we have process 0, process 1, and process 2. They all invoke an NQ operation, and then process 0 invokes a DQ, and then process 1 invokes a DQ. So at time step T1, we're going to analyze the method calls up to this time step. So we first set up our column vectors, and item 7 corresponds to position 0 of the vector, item 8 corresponds to position 1 of the vector, and item 9 corresponds to position 2 of the vector. And so NQ7 and NQ8 both overlap. So we don't know which one happens first. So they're both assigned a value of 1. Now NQ9, its invocation happens after the response of NQ7. So it needs to be demoted. And so it's going to be assigned a 1/2. So then we add the vectors and we get 1, 1, and 1/2. So what we're looking for is that these values are greater than or equal to 0. If they go below 0, that means that something is incorrect in the history. So we are still correct at time step T1. And then at time step T2, we have a DQ8. So we're going to assign this a -1. So when we add up the vectors, we get 1, 0, and 1/2. So we're still greater than or equal to 0. So we're correct at time step T2. Then at time step T3, we have a DQ7. So the 7 had previously demoted the 9. So our NQ9 has to be promoted back to a 1. And the DQ7 is assigned a -1, and we add the vectors, we get 0, 0, 1. So this indicates that we are correct up to time step T3, and that there's only one element left in the queue, and that's item 9, and it has the highest priority to be removed from this queue. So we designed a dynamic analysis tool and provide lightweight functions to the user for representing these method calls in vector space. So the tool launches a verification thread that runs simultaneously with the program, and it's going to read all these user-specified method calls, and it's going to construct the vector space representation of those method calls. So we have some predefined semantics, which include first in, first out, last in, first out, set, and map. And then we have the operation types, which is producer, consumer, reader, and writer. So the create method is what would be called after a method is invoked, and you would pass in the key of the item, the value of the item, the semantics of the data structure, the type of the method call, and the invocation and response are a timestamp measured as a long int, and then the result, which is a Boolean. And then what this does internally is it inserts it into a thread local list, and the verification thread is going to handle those method calls. The insert method is what advances the thread local list iterator. And so this gives the programmer some flexibility on when those method calls become visible to the verification thread. So we also extend this theory to support transactions, and we apply the promotion demotion scheme if the method calls M1 and M2 are in the same transaction. T1 and M1 happens before M2 and T1, or if method call M1 is in transaction T1, method call M2 is in a second transaction T2, where T1 and T2 are different transactions, and T1 happens before T2. So we provide the insert transaction function, which allows the user to make the entire transaction visible to the verification thread, and then the rollback transaction, which discards the method calls in case the transaction aborts. So to support durability, our verification analysis is performed separately. So we maintain the vector space method calls for methods performed cache side, and then we have a separate vector space analysis for the method calls that have been explicitly persisted using the cache line writeback and sfence. And so we provide the same method calls, but they have an underscore persist for that particular reason. So there's a couple of different design strategies that we had to support with our tool. The first is a recovery procedure. So the cache line writeback and fence are very expensive. And so the designers will often use those instructions to just persist the bare minimum of information to be able to reconstruct their data structure using a recovery procedure. This was done by Petra. That was a transactional, persistent transactional approach. They only explicitly persist a log of transaction operations. And for in linked data structures, they only persist the nodes, and the nodes are made accessible without persisting the link. And this is done by link-free data structures. So these design strategies will use the recovery procedure to reconstruct the data structure. And so when that recovery procedure is called, we call the VSVD functions after the successful recovery of an operation or a transaction. Another design strategy is an explicit write-back for a range of memory locations. Some approaches will do a write-back for many many different memory locations at the same time. This is done by one file or Romulus, and it's very difficult to know exactly which operations have been written back to persistent memory during these persistent write-backs. So what we have provided to the user is an insert persist map, and this maps a method call to a pointer address. So when the range of memory locations is persisted using a persistent write-back, we provide the handle persist write-back function, which can look up that pointer address and figure out which method call that was associated with. And then it's going to call the create method persist that's going to show to the verification thread that this was persisted, and it erases it from the persist map. And then if there's anything left in that persist map, then that indicates that there were method calls that were not persisted. So for our correctness verification, for linearizability, the verification thread will cycle through those thread local lists, and it will analyze the method calls up to the method call with the slowest response time. This is because we don't want to lose information due to a delayed thread. And then we have to include any overlapping methods, since those methods that overlap can affect the outcome of that method. And then we each cycle through the thread local list is a time step. And the history is linearizable if all elements of the vector sums are greater than or equal to 0 at every time step. So for durable linearizability, we're maintaining two different vector space analysis for the methods performed cache side and the methods performed that have been explicitly written back to persistent memory. And we're going to compare the vector sums at the end. And if the vector sums for cache side method calls is equivalent to the vector sums for the explicitly persistent method calls at every time step we're following the recovery procedure, then the program is durable linearizable. So here's an example of how it works internally. We have each thread local list, and then we have an iterator into that list. And we have to identify the slowest response time. So this, in this example, is M3. And then we have to include all methods that overlap with M3. So in this case, it's going to be M1, M2, M3, and M4. And so the verification will be performed up to those four method calls. And then the other method calls will be handled in the next time step. So we applied our durable linearizable correctness tool to transactional durable data structures. We evaluated Petra, Romulus, OneFile, and PMDK. And then we also applied our tool to durable data structures. We tested efficient durable sets, that's also referred to as link-free data structures, and also log-free data structures. So here's the performance results for the verification times of durable data structures. The x-axis is the number of method calls, and the y-axis is the verification time in seconds. And so we check linked lists, skip lists, maps, and binary search trees. So the time complexity that we get is n squared. And so for sets and maps, when we don't need to do the promotion demotion because the order of the item in that map or set doesn't matter. But if the method call fails, we have to go through every method, and any method that shares the same key with the method call that failed, we have to demote that method call, and that's so that we can verify that that failed method was correct. And that additional for loop makes the time complexity n squared time. So we also tested transactional durable data structures, and we tested linked lists, skip lists, multidimensional lists, maps, and binary search trees. And here we get an n trend line. And the reason is because we assume transactional atomicity, and this is where the either all of the operations succeed, or if one fails, then the entire transaction has to abort. And since we could just discard the aborted transactions for durable linearizability extended to transactions, we didn't need to justify the aborted transaction. So we didn't need that additional for loop. And that's why we were able to achieve an n time complexity. So we detected some correctness violations in Petra. The logical interpretation of the node's existence in the set ignored the operations that were a part of that calling thread's active transaction. So we were able to notify the authors of this logical interpretation, and it just required an initial check with just some like an if statement. So it was a very easy fix. The other was with Romulus in one file. It allowed transactions with failed operations to commit, which violated transactional atomicity. So we resolve this by explicitly throwing an abort exception in the user code if an operation failed in that transaction. So we don't consider this to be a flaw in Romulus or one file because all they do is they execute a user code transactionally. They don't handle the semantics of that user code. And so since we assumed transactional atomicity, we had to add in that functionality into the user code. So this is an example of how our tool was used to identify flaws in the user code. So in conclusion, we've presented a durable, linearizable correctness tool. We've presented an efficient technique that models a happens before relation between method calls and vector space. And we provided a technique for handling very common design strategies for persistent memory data structures, which includes the recovery procedure and also an explicit write-back for a memory location range. We've achieved an O of n squared time complexity when checking the durable data structures, and we've achieved an O of n time complexity for checking transactional durable data structures. That's the conclusion of my presentation. Are there any questions?
Christina, was amazing presentation, but I have a few questions, and I think that you will think they're stupid questions, but I still want to ask them. So as far as I understand, you have the code, and then you go into this code and you insert these calls to your framework, like the markers, and then you run the code, and then the code goes and it makes calls to your framework and informs your framework about what's going on in the code. Am I right?
That's correct.
Okay, and then my question, okay, it was not a stupid question. So that's probably going to be, the next one. So is it possible, did you think about the possibility about taking the code and automatically injecting these instructions there? Because right now I understand you do it manually, but is it possible to do it automatically?
Yes, this could be done through a compiler technique. That is definitely something of interest. My research background is not in compiler techniques, but this is something that we could definitely do with perhaps with a co-author that had some experience with compiler techniques. We could automate that, the ability to inject these auxiliary the calls that would take those methods called by the user and convert them to the vector space equivalent. So this is definitely a possibility for future work.
And do you think it's possible in general to do? Because now it's manual, so maybe there has to be human judgment every time, so the person has to decide where to put, or you think it's possible to make some rule for these decisions?
So I think it could be done if the with the data structure method calls. I think it would be straightforward to automate the cache side method calls. Where it gets a little bit more complicated is with the explicit cache line writebacks and fences, because sometimes the usage of those is done so that it's hard to know exactly when the method call has been persisted. And so that might take a little bit of extra work in trying to figure out how to automate that process.
Mm-hmm. And do you think it's possible to apply your method and your idea to maybe detecting memory leaks? Because it's a very common problem as well. Because in your research, you're addressing the problem of a memory which you don't want to, the specific memory you mentioned. But maybe it's applicable to the memory leaks in general, where people allocate memory in one place and forget to release it in another place.
Yeah, I think that that we could definitely do with somehow tracking the allocation, perhaps even in vector space, where we're able to manage in vector space when memory has been allocated and when it's deallocated, and we can detect when there's a memory leak of some sort. So I think that that would be another extension to perhaps checking memory management techniques.
So what do you think, my next question, what do you think is the core innovation in your research? I think that's the model which you designed on the vector space. That's your innovative part, right?
Yes. Yeah, using vector space to be able to efficiently check for correctness properties, and in this case with durability properties, since the persistent memory design, it is more costly, and so we want to make sure, and it's also, it needs to be recoverable, and so our tool can be used to ensure that that recoverability can be maintained. So I think that that definitely elevates the importance of the tool, is for the ability to provide recoverable code. That expectation is very important.
Right. And then another question for one of the YouTube viewers, they're asking, is it possible to use this vector model for general purpose distributed systems, not only for NVM storages? Kind of similar to the question I asked. So can we make it more generic, your vector model?
Yes, yes, it can be more generic. We can check just standard correctness properties such as linearizability for multi-core programs, and it can be extended to other correctness properties as well, just with determining how the method calls are supposed to be ordered between each other. So we can definitely extend it to that functionality as well. So it does have practical applications for correctness verification for the more general programming.
Yeah, it seems like injecting those instructions into the Java or C++ code or Python code, it's pretty engineering task, and it's not so difficult to do that. But what's more interesting is actually taking this information from there and then do the analysis you do. So it's like two separate problems, right? So the first one problem is quite engineering. So we just take Java programmer and ask that people to inject the instructions. So,
yeah, and the other thing that I wanted to mention was that right now we handle your standard producer, consumer, reader, writer method. So that we need to extend to other types of method calls, and like, for example, account semantics. We would want to be able to check that an account balance was correct. So we would want to be able to be able to provide that sort of correctness verification for other types of method calls as well.
Mm-hmm. All right. So it sounds like it's very interesting research. And again, my question, how long did it take, and do you have it in open code, in open source?
Yes, I have it available open source. And so if I'm not sure how to make that available to everybody, so perhaps maybe you can email me and let me know how to make that available.
I will. And how long did it take? Like, how big was the project?
The project, it took, I think it took over 6 months. I think that we had started some work with a previous paper, and then we kind of kept extending that previous paper, and so it kind of started evolving, and then it became into the paper that it is today. So, but the time that I had decided we're going to check durability properties, that took about maybe seven months from that point to the finish line.
All right. Thanks a lot. Thanks for coming. And I know you're far away from us, so this is early morning for you. So thank you for waking up so early and attending the conference. Thanks for submitting the paper. I hope to see you next year. Bye-bye.
Okay, thanks.